Good morning, everybody. How is everybody doing this morning? Hopefully you guys had a good night's sleep and are ready to go. We are going to be continuing to talk about gases and gas laws and also talking about absolute zero today. And look at that. Already technical issues. All right. Already having technical issues this morning. Lovely. So I don't see anybody right here watching right now. All right, wait, we got a couple back. All right, so sorry about that. I don't know what's going on. Technical issues again. It's just, I don't know, corona problems. So let's go on and let's start talking about gases. So Jonathan's here. Hi, Jonathan. Anybody else? As I was saying, I don't know at what point in time I got cut off, but as I was saying, we're going to be talking about a couple new gas laws today. We're going to be talking about temperature and absolute zero, and we're going to talk about how gases, actually the study of gases, led to the discovery of absolute zero. Okay, so before we do that, let's talk about the homework. You guys had to solve several of these problems that were related to Avogadro's law. And that's got to do with moles and how moles are related to the volume of a gas and the pressure of a gas. Now, we should, as we solve these things, think about the relationships and what causes these relationships to take place. All right. Hey, Leo, how's it going? So as we're doing this, we kind of need to make a mental note of what these different laws are and how they work. All right, so we've talked about Boyle's law, we've talked about Avogadro's law, and we're going to talk about some more today. Okay, and so it's good to just keep in mind how these things work. All right, and so before we even talk about the homework, let's just go over Boyle's law, right? And Boyle's law, let's use red here. Boyle's law basically said, right, as the pressure goes up, the volume goes down, right? So pressure and volume are inversely proportional, and that gave us the law of pressure times volume is a constant, or P1 V1 equals P2 V2. And we notice that when things are inversely proportional, they have a constant product. Okay, that's Boyle's law. And then we saw Avogadro's law, and we saw kind of two different forms of it. Avogadro's law, right? And he said, basically, as you increase the amount of moles, as you add gas in, as N goes up, then you're going to see either, or a combination of both, the volume going up. Or you could say as N goes up, then the pressure goes up, okay? And we saw that's a direct proportionality. And so if you have a direct proportionality, then you have this, it's a constant ratio, right? So there are constant ratios of N and V. So that would be N1 over V1 equals N2 over V2. Or you could flip them, right? Or it would be, let's say, N1 over P1 equals N1 over P2. And let's make some sense of these. Simply put, if you add more stuff, if you add more particles, those particles are probably going to be taking up more space, right? So as you add more particles, the volume should increase. Or if the volume stays constant, as you add more particles, those particles are going to bump into things more often, and that's going to cause an increase in pressure, because pressure is caused by things bumping into things, right? And then we saw up here, if we increase the pressure, that's going to cause the volume to go down, right? So if we press down on a gas in a piston, increasing the amount of force on a piston, that's going to decrease the volume. Or conversely, we could say if we somehow increase the volume, that's going to make the pressure go down. Why? Because the particles are further apart and they have fewer collisions, which means a lower pressure. Okay? So today we're going to be looking at a couple other laws, and their relationship with temperature. And so temperature is kind of the main thing today. So we're going to get back to temperature here in a little bit, and we're going to talk about Charles's law. Charles's law, and get to that here in a little bit. But before we do that, let's jump back into the homework. How's it going, Max? And Dark Ranger. Don't know who that is, but that's a cool name. Dark Ranger. All right. So let's get into the homework from last time. So I have a lot of problems. Sorry about that, guys. But anyway, it's just practice for things, decreasing, increasing number of moles, all that kind of stuff. So without further ado, let's see. A balloon contains that's a very small amount of gas, but, it's somewhat normal. So this is going to be our N1, is going to be 0.0098 moles of helium and has a volume of 186 milliliters. And that is going to be our V1. But of course, we always want to have our volume in liters. But let me see, I think we can just leave it in milliliters in this case because there's no other volume here. We're going to be solving for volume. If 0.033 moles of helium are added to the balloon, what is its final volume? So we have, this is not N2, but this is how much we're adding to it. So this 0.033. So N2 is going to be equal to 0.0098 plus 0.033. Okay? And so that, we can go ahead and calculate that to calculate N2. 0.0098 plus 0.033 to get us a final number of moles of 0.0428 moles of helium. All right, and we want to know what the final volume is. So what is the final volume? So we are solving for your V2. That's what we want to know. And we can use we could probably just use the rearranged equations that we have up here, all right? Or we could just go ahead and start over and think about the original Avogadro's law, which is V1 over N1 equals V2 over N2. And if we're solving for V2, we're going to multiply both sides of the equation by N2. That's going to get us V2 equals V1 N2 over N1. So we just plug in the numbers. That's going to be 186 milliliters. I misspoke earlier. We can just leave this as milliliters. If you want to convert it to liters, that's fine. But we can leave it as milliliters as long as there's no other units it needs to cancel out with. N2 is 0.0428 moles. And our initial number of moles is 0.0098. Our moles over moles cancel, and our answer should be in milliliters. So that's going to be, I'm just going to leave this number in my calculator, that 0.0428 times my 186 divided by 0.0098 to get me 812. I have three significant figures, so I'll just round that off to 812, and my units are still milliliters. 812 milliliters. Okay? Questions on that? And I'm just looking, I don't see any questions here in the chat. We're going to just continue on, go through these. As soon as you have a question, just stop me, ask me a question right there in the chat. Otherwise, I'm going to continue on and solve these. Okay? So, the key thing here to remember is just that N2 is going to be adding this number because it's saying that keyword of added. You have to add in that number to N1 to get N2. All right. Number 4, you have a balloon. It's got a certain number of moles of air. In this case, a lot more than the previous problem. So 2.55 moles of air. And that's going to be our N1 in this case. And a volume V1, how much air should you remove in order to decrease the volume to 45 liters? This 45 liters is our final volume, but we want to know how much air that we should remove, okay? So it's like, you know, it's some kind of balloon. We're just going to let out some of the air. This is fairly large, so we're thinking, okay, this is some kind of huge weather balloon that we want to just decrease the volume of, something like that. All right? So the final addition of subtraction, we're going to be doing that at the end because we already have our N1, V1, and V2, and we're going to solve for N2. We just need to keep in mind that N2 is not our final answer because we don't want the final number of moles, but we want the amount that we should remove. So that's going to be an N1 minus N2 in order to get the amount that we should remove. So to solve for N2, we could use the previously rearranged equation, although I don't think we have one specifically for that, or we could just use the Avogadro's law. And in this case, because we're solving for N2, I'm going to want to make sure my N is on top. Rather than writing it this way, I'm going to write it this way with N1 over V1 equals N2 over V2. Okay, we talked about why that is mathematically, and you can prove that this equation is exactly the same as this equation, and you're allowed to flip those. That's fine. So that being said, we want to solve for N2, so I'm going to do that by multiplying both sides of the equation by V2, which is going to get me N2 equals N1 V2 over V1. Okay? Now, N1 is 2.55 moles. V2 is 45. And V1 is 56.7 liters, okay? Liters over liters, so make sure your units are the same, which they are there. Liters over liters, they're going to cancel, and our final answer is going to be in moles. 2.55 times 45 divided by 56.7 gets us 2.02. 2.02 moles of air. Okay, but that's not our final answer because remember it says how much air should we remove. All right, that's what the question's asking, and so all that really is saying is, okay, you know, in order to get down to 2.02 from 2.55, how much do we need to take out? So that's going to be a subtraction. Okay, so our final answer is going to be N1 minus N2, so that's going to be 2.55 moles minus this 2.02 moles, right? And you can do that in your calculator, or it's just going to be 55 minus 2, right? Because the 2 over 2 minus 2 is going to cancel out. And I think we're going to be ending up with only two significant figures, which happens sometimes when you have a subtraction, okay? And so that's going to get us 0.53 moles as our final answer. Okay? All right. So that's the front page. Any questions on that so far? How many people we got? Oh, a whopping 5. Everybody else is sleeping and they're going to come in later, which is fine. All right. But that's great. Okay. So if there's no questions, I'm going to go ahead and jump on to number 5 here, which is, once again, a balloon. And this time, we want to see how much gas should we add in order to double its volume. How much gas should we add in order to triple its volume? Now, this one is actually not too bad at all. We don't need to know what the volume is at all, okay? So don't worry about that you know, there's no volume written down or anything like that. We don't need to know that. All we need to do is understand the law behind the equation. And when you understand the law behind the equation, you can just try to just think about what's going on. So remember that as you increase the amount of gas, you're going to increase the volume. As you increase the moles, you're going to increase the volume. In fact, they're are linearly related. Right? That was the first thing we discussed. And so that means that if we want to double its volume, that means we want to double its moles of gas, okay? And so what does that mean? So how much should we add in order to double its volume? Well, that means we're going to add 0.22 moles of gas, right? Because if we add the same amount of gas that you start with, that will double the amount of moles of gas, and that's going to double its volume, okay? What about if we want to triple its volume? Well, then we want to triple its moles, and so we're going to add 0.44 moles of a gas, right? Why is that? Because if we start with 0.22 and we add twice as much, so we're adding 2 times the amount of N1, right? So we're adding 0.44 moles, then we're going to end up with a final, your N2, in this case, is going to be 0.66 moles, which is what? 3 times as much as your N1, okay? And that means we're going to triple its volume. All right, that's the best way to solve a problem like this. I know sometimes you just want to plug everything in an equation, but that's going to make it more difficult. Just think through about what that means. What does it mean to double its volume? All right, that means we're going to double its moles, and that means we need to add the same amount that you start with. Okay? So that's the best approach to number 5. Number 6, we have a sealed contains. Well, that's a typo. A sealed container. Sorry about that. A sealed container has 0.22 moles of a gas. All right. And when it says sealed, we're thinking, well, what does that mean, sealed? That means that this is going to be probably some kind of hard container, and then we're going to be thinking about it's a constant volume situation, okay? So we have this sealed container, it's got 0.22 moles of gas. How much gas should you remove in order to reduce its pressure to half? So this is exactly what's going on. We want to reduce the amount of pressure. And so same kind of situation as here, because we don't have an initial pressure and a final pressure or something like that, we just know that we want to decrease the pressure to half. We need to think through what's going on. So if we want half of the original pressure, that means we want half of the amount of gas. So reducing the pressure to half means that we want to reduce to half of the moles of gas that we started with. All right? And so if we're going to reduce to half, how much gas should we remove? That means we're going to remove half of it, or 0.11 moles of gas. Okay? And that means we're going to end up with, if we remove 0.11 moles, we're going to end up with 0.11 moles, and that's going to be half the amount of gas that we started with, and that's going to give us half the pressure. All right? So once again, thinking through what's going on makes this a little bit easier to solve than trying to plug it in a calculator. All right. Not last. We got 2 more questions. We got another sealed containers filled with 18.64 moles of propane and has a pressure of 96 psi. And if we have 7.5 moles of propane removed, what's the final pressure? So this is kind of like a propane tank, all right? And this is totally understandable. So this is going to be as you're burning the propane, which is ridiculously cold outside for being the end of April, and we still have our heat on, which is making me cry. But anyway, can't believe that it's this cold in April, but it is. So at least here in Connecticut, I don't know where, if anybody else is listening from some other part of the world, but whatever, it's cold here, which is crazy. So this is a propane tank, all right, and you have an initial pressure, which is going to be what you're reading on the gauge, right? So pressure 96 psi, that's a normal number that we might read from a gauge. We're removing a certain amount of moles of propane, probably to burn them. What's the final pressure? So let's just identify some stuff and then go on. This is my N1. This is my P1. And if I'm removing this, that means my N2 equals N1 minus that. So it's going to be 18.64 minus this 7.5. Okay? So let's just get that 18.64 minus 7.14 moles of gas. And we want to know, well, what's the final pressure? So we have, if we're solving for P2, we want to get the form of the equation that enables us to have P2 on top. So that's going to be P1 over N1 equals P2 over N2. Remember, constant ratio, because N and P have a linear relationship. They're directly proportional. So if I want to get P2 all by itself and multiply both sides by N2, that's going to get me P2 equals P1 N2 over N1. Plug in the numbers. P1 is 96 psi, which we can leave as psi because we're just going to get our answer in psi. N2 is 11.14 moles. And N1 is 18.64 moles. Let's do that calculation. So that's our 11.14 times 96. So multiply numbers on the top, divide by numbers on the bottom, divide by 18.64. That's going to get me 57.4. So just round that off to, well, we really only have two significant figures, but it starts with a 9. So you could just say 57. Anyway, so 2 sig figs, so you got 57 psi for that one. Okay, 57 psi. So you still have enough propane to last you for a little bit. All right. I don't see any questions, so I'm going to continue on to the last one. And that is, we have a sealed container, once again, filled with 0.75 moles of acetylene. Acetylene, which is also used for burning, but typically a higher temperature acetylene torch kind of thing. And it has a pressure of 8.9 atmospheres. If the pressure goes down to 2.55 atmospheres, how much acetylene has been removed? So this is going to be our N1. We're going to solve for N2 and then figure out the amount that's removed. This is our 8.9 is our P1, and the pressure is going down, so this is P2. So we want to know, we're first going to solve for N2, and then we're going to subtract N1 from N2 to get the amount removed. So that's going to be, once again, we have N1 over P1 equals N2 over P2. To solve for N2, multiply both sides by P2, says N2 equals N1 P2 over P1. N1 is 0.75 moles. P2 is 2.55 atmospheres. And P1 is 8.9 atmospheres. Atmospheres over atmospheres cancels out. It's going to get me moles as my final units. So 0.75 times 2.55 divided by 8.9 to get a final answer of 0.215 moles. But I misspoke. That's not our final answer. That is N2. So how much acetylene has been removed? It should be N1 minus this. So your final answer is N1 minus N2, which is 0.75 minus 0.215. All right, so that's going to be 0.75 minus that take it as 0.535. And then a bit tricky here, we should have only two significant figures. So because we, it just says 0.75 moles, so we're just going to leave this as 0.54. And if you wrote 0.535, no big deal there. But I'm going to say 0.54 moles of gas or moles of acetylene removed. Okay? So that's the whole homework. Are you guys still with me? I see, oh, we're getting more people here. Awesome. So for those of you who are with me, any questions on the homework at all? Because that's it. We're done. And we can start the new stuff here. All right. I know it was a bunch of problems, but they weren't too bad. None of the problems was extremely involved. So hopefully you guys all got these right. Anybody get anything wrong or, and still have a question about it? Okay. Maybe people are sleeping because they know they got them right and they're going to come back and watch this at 2x speed, which is what I would do half the time. But anyway, let's go on to the new stuff. So the new stuff for today is more stuff about gases, and I'm going to try to actually put together a lab that you guys can do. So maybe me and Gloria, we're going to show you guys a lab that you guys can do, and we'll talk about that next week sometime. So I'm thinking our test is probably not going to be next week. I'm thinking the week after. All right, and so we're going to do some more gas laws. We're going to do an ideal gas law, combined gas law, and then do a lab. And so I'm not planning on having a test next week, so no test next week. All right, if you guys are wondering about that. Okay, so new stuff. Let's get on to Charles's law. All right, so we talked about Boyle's law, we talked about Avogadro's law, and today we're going to talk about Charles' law. And Charles was a pretty unique individual. Okay. Oh, I had a question here. Could you go over number 6 on the new homework? I don't think so. I think we'll be doing that next time. If you are that far ahead, you're awesome. But we will get to some of the questions on the new homework. I don't remember. Maybe, I don't remember which ones we're going to get to, but we'll get to some of them. Number 6. Oh, yeah, you know what? Nah, I don't think so. I think we're going to do, I'm going to get through 5. So anyway, let's talk about the law here. So Charles' law, Charles was a unique individual, and Charles was a scientist, but he was also a guy that was a lot into your high adventure sports kind of thing. All right, and so he was a pretty adventurous guy. So he actually created the very first helium balloon, or actually, I'm sorry, it wasn't a helium balloon, it was a hydrogen balloon, or a lighter than air balloon. But not just for like birthday parties and stuff, but he made it to fly in. And so this is like the first ever flight that, of a craft that had ever been produced, ever, okay? And so he filled this balloon, and what he did was, I'm going to go ahead and just write on here anyway, even though this is not Charles' law. What he did was he reacted iron, and he reacted it with, I believe it was hydrochloric acid. It was some kind of acid. And when it reacts, it's going to make iron chloride, FeCl. I believe it's iron 2 chloride, but anyway, he didn't really care about that. And it made hydrogen gas. All right, and that hydrogen gas he collected. So he used like a lot of iron, right? And he mixed that with a lot of acid, and he made enough hydrogen gas that he filled a balloon, like filled a huge thing that looked like the size of a hot air balloon. All right, so filled balloon. And after he did that, he's not crazy, so he didn't actually get in it the first time, but he just filled it and put it, I don't know what he put in it, just like, a sack of potatoes or something like that. I'm just making that part up. But he filled it with something, and then he set it off, and he just let it fly. And it flew, and it flew, and it flew, and it flew miles and miles away. And then when it landed somewhere, it landed in the middle of some guy's farm. And then in the middle of some guy's farm, this guy saw this thing coming from the sky, landing in his farm. He called all his buddies, and they came with pitchforks and destroyed the thing because they thought this was a UFO and aliens coming down, right? No, literally, they did. And so Charles unfortunately had to rebuild his whole balloon, but he said, okay, this is a success. And so he rebuilt the balloon, filled it with hydrogen gas, and then he got it in it himself, and he flew around, and he made sure that he had some people on horseback follow him around so that whenever he landed down, he wouldn't get attacked by farmers with pitchforks. And so he did survive that, which would have been the very first flight had the farmers not destroyed his balloon. But it turned out that some other guy was competing with him and made a hot air balloon at the same time and beat him. And so Charles was the second person ever in flight, in a flight of some kind of balloon or any kind of flight. He was beat by some other guy because the farmers destroyed his balloon. So I always thought that was a bummer. He should have been the first one ever to fly, but he was like the second one. Anyway, so let's go on and talk about his law. So Charles' law, he basically studied temperature and volume. And so temperature and volume, all right? And so what he noticed when he increased the temperature, so you have some kind of gas, and then if you heat it up, as you increase, let's do it this way. So as you increase the temperature, what do you think is going to happen? The gas particles are going to be moving around faster and faster, and when they move around faster, they're going to have more collisions, and they're going to be bumping into stuff with more power. That's going to cause the volume to increase, okay? Which also leads me to another guy's law. It's a Gay-Lussac's law, which is, so let's write it down here. So this other pair of scientists, Gay-Lussac's law, right, is very related to this. And these guys studied the relationship between temperature and pressure and basically said, okay, as I increase the temperature, right, that's going to cause those gas particles to move around faster, to bump into things more often, and to have stronger collisions. That's going to make the pressure go up. Okay, so we have two different laws that are very similar. As the temperature goes up, the volume goes up, or as the temperature goes up, the pressure goes up. Okay, and you can have them both go up together, but that would be a little bit of a more complex law that we're not going to look at today. Okay, so either Charles' law, which is this, okay, as the temperature goes up, the volume goes up, or Gay-Lussac's law, as the temperature goes up, the pressure goes up. And we can really quickly turn those into usable equations, because we already know what does it look like when two things are directly proportional. What does that look like? It looks like they have a constant ratio, right? So you could have that as V over T is a constant, or you could have it as T over V is a constant. And we can go ahead and turn that into a variety of different equations, okay? Which I'll do here on the back, all right? So if you have, let's say, as your temperature goes up, so temperature is proportional to your volume. As the temperature goes up, the volume goes up. What does that mean? That means that the temperature equals some constant times the volume. So I'm going to divide both sides by V. So this is going to be temperature over volume is going to be some constant. And well, if temperature over volume is constant, that would mean that T1 over V1 equals T2 over V2, because you have a constant ratio. Anytime you have direct proportionality, that means you have a constant ratio. And you can express that constant ratio like this, or you can express it like this, V1 over T1 equals V2 over T2. So this is form 1, this is form 2. Or if we're talking about the Gay-Lussac's law, we're going to look at exactly the same kind of relationship, and we just flip out V for P. And that's going to look like this. That's going to look like, let's write it right over here. It's going to look like T1 over P1 equals T2 over P2. Or it's going to look like P1 over T1 equals P2 over T2. So there you have 4 different equations. Okay, and you can even think about, well, how are temperature and moles of gas related? And I'll go ahead and touch on that now too. Okay, so if you have a situation like a hot air balloon, well, what happens in a hot air balloon? In a hot air balloon, you increase the temperature And the volume doesn't change, the pressure doesn't change. Instead, the number of moles of gas changes. So if you have a situation like a hot air balloon where you have temperature and moles of gas, well, what do you think is going to happen? That takes a little bit more thought in terms of what's going on. But if you increase the temperature, so let's say we increase the temperature and our volume stays the same and the pressure stays the same, what happens is these gas particles, they move around faster, they spread out, and because they're spreading out, that means that the number of moles must go down, that you must somehow have gas leak out. And you can, think about what's going on when you heat up the air in the hot air balloon. Some of that air is expanding, and so it must be leaking out of the balloon, so the number of moles are going to decrease. And so you can set up a law between the temperature and the number of moles of gas because they're inversely proportional. That would mean, right, so temperature is proportional to 1 over N, right? Or you could say that temperature equals K over N, or put all your variables on one side. So that's going to be NT is going to be a constant, and that's going to get you a law that's very similar to Boyle's law, and that's going to be this: N1T1 equals N2T2. Okay, so we've dealt with temperature there, right? Temperature and number of moles, temperature and pressure, and temperature and volume. And that's a whopping 5 equations. But thankfully, you guys don't have to memorize the equations. But anyway, I want you guys to understand these relationships, to think about what exactly is going on here. All right? But before we do that, we have to go back to Charles's law. And we have to say, all right, well, what was Charles doing when he did this law? Really, really cool. So what he was doing when he did this law, this relationship of temperature and volume, is let's do it this way. Okay. So let's say he graphed temperature versus volume. I don't remember exactly what graph he made, but he was graphing temperature versus volume. Okay. And then so he did this, and let's say he's got a whole bunch of measurements that are like out here, and like this. All right. He noticed that it was a linear relationship. Okay. But he literally just stopped there. So he's like, okay, I've got this, and I don't have it. Let me see if I can use this as a straight edge. And he said, well, I don't. He just cared about this linear relationship, and he's like, all right, this is really cool. That as the temperature goes up, the volume goes up. We've got this linear relationship thing going on here. And yeah, really, really nice. As the volume goes up, temperature goes up. As the temperature goes up, volume goes up. Or as the temperature goes down, volume goes down. All that kind of crazy stuff. Well, he didn't go any further with this. It took the likes of Lord Kelvin about 100 years later. Lord Kelvin came on the scene. He's like, oh, that's a neat graph. What if I take this data that Charles looked at and I extrapolate down to 0. And so what he said, all right, I'm going to take this and I'm going to extrapolate this all the way down until we get to a 0 value for your volume. All right. And so when he got down to a 0 volume right here, then he said, well, that must be at 0 volume, that must be the coldest possible temperature. The temperature at which a gas would have approximately 0 volume. And obviously you can't have 0 volume for a gas. At some point in time, that gas would turn into a liquid and turn into a solid, and those atoms or particles would take up space themselves, right? But theoretically, we're saying at 0 volume, that's going to be the coldest possible temperature. And Lord Kelvin said, well, that is going to be absolute 0. And for the Celsius scale, they discovered by by looking at this graph, Lord Kelvin discovered that this was negative 273 degrees Celsius. Well, I don't know if he got that exact number, but eventually we've gotten to a pretty good number. So it's negative 273 degrees Celsius. Okay? So that is your value of absolute zero on the Celsius scale. And because this was the work done by Lord Kelvin, now the whole scale, the whole temperature scale is named after Kelvin. And so Kelvin, absolute zero, is negative 273 degrees Celsius, but it's also 0 K. Looks like OK, but it's not. It's 0 K. And it's not OK to write 0 degrees K. You don't write degrees for Kelvin, which I don't really know why, but they decided for Kelvin, we don't want that stupid degree symbol. We're just going to use this units of K. So that's how you write it. Any temperature in Kelvin, you just write the number and Kelvin. You don't write degrees Kelvin. All right. So if you're converting between Celsius and Kelvin, which you need to do in these problems, let's go ahead and jump into the new homework here. Oh, time is flying. What do you do? So if you need to convert between Celsius and Kelvin, all you do is for degree Celsius to degree Kelvin is you subtract 270, you add 273 to go from Celsius to Kelvin, or you subtract 273 to go from Kelvin to Celsius. Okay? So for this one, 10 degrees Celsius is equal to 283 Kelvin. All right? And then you guys can solve the rest of those. I want to go ahead and solve numbers 4 and 5 here if I have some time. Number 4, we have 1 liter of gas. It's at 100 degrees Celsius, and it's cooled to negative 100 degrees Celsius. What's the new volume? Here's the key thing, and I know I waited till the last minute to tell you guys. Anytime you solve these temperatures must be converted to Kelvin. Okay? You must always convert temperatures to Kelvin. So you will get some crazy answer like negative volumes if you don't convert it to Kelvin. So 100 degrees Celsius, you need to convert that to Kelvin. So you add 273. So this is going to be negative 100 degrees Celsius. That's going to be 173 Kelvin. Okay? And so we're solving here for V2. What's that going to be? And this here is going to be V1. So we have our relationship, and that is for all of these that we're going to put volumes on top. V1 over T1 equals V2 over T2, which means if we're solving for V2, I'm going to multiply both sides of the equation by T2, which is going to get me V2 equals V1 T2 over T1. Okay? So I need to plug in some numbers. That's going to get me V1 is, so that's just simply 1 liter. T2 is, what's T2? Where is T2? Oh, this one's T2. So this is T1. This is T2. T2 is 173 Kelvin, and this is over 373 Kelvin. And so 1 times 173 is going to be 173 divided by 373, and that's going to give me 0.464. We have 2 sig figs, so it's going to just be 0.46, and that's a volume. So our volume is 0.46 liters, our final volume, okay? 0.46 liters. And does that make sense? Well, you're cooling it down. If you're cooling it down, we're expecting those particles to move slower and slower, take up less space because they're moving slower. And that's exactly what's going on. And it's a little bit less than half, which is exactly what we expect because the temperature is a little bit less than half of the initial temperature. Okay? And I know we're kind of out of time. Let me see. We're out of time, but let me see. Do I have time to do this one? Sure. Let's just do number 5 real quick. Number 5. Yo, teacher, I ain't in this class. Can you explain theoretical yield? I have an excellent video that explains theoretical yield, all right? And that's going to be percent yield made easy. So you just type in percent yield made easy and you'll find it, Okay. I do want to, I have another class here in 4 minutes, so I want to just quickly solve this one, number 5 for you guys. All right, and that is, if you have, you know what, we did question number 6. You know what, I'm going to skip down, I'm going to do number 6, because I know we did question number 6. There are 2 moles of gas in an open container at 20 degrees Celsius, so right now we're thinking 2 moles of gas, that's going to be our N1. 20 degrees Celsius, we need to convert that to Kelvin, so it's going to be 273 plus 20. That's going to be 293 Kelvin. That's going to be our T1, right? The container is heated to 40 degrees. That's going to be our T2. And now we're increasing that by 20 degrees. So it says 40 plus 273. That should be 313 Kelvin. How many moles of gas remain in the container? So this time we're not asking how many moles of gas are removed. We're literally asking how many moles of gas remain in the container. So we are solving for N2, right? We are solving for N2 in this case, which means if we're solving for N2, we have the relationship between moles of gas and temperature, and that is N1 T1 equals N2 T2. Solving for N2 is we're going to divide both sides of the equation by T2. That's going to be N2 equals N1 T1 over T2. So my N1 is 2 moles. My T1 is 293 Kelvin. T2 is 313 Kelvin. And that's going to give me my final answer. Let's see, 2 times 293 divided by 313 gets me 1.87. Oh, and we only have 2 sig figs, so 1.9. 1.9 moles. That's it. That's your final answer. That's how to solve that kind of problem. All right, we're done. See you guys. I got to sign out. I got another class in 1 minute. Cool. See ya. Have a great day, Badger.